So this is an example of a problem where we're dealing with angled shots, but we're also dealing with that change in elevation that you're dealing with the practical exam. So just kind of talking you through the ideas, making sure you get the concept right here again. None of the concepts really change. It's just a matter of applying them correctly in terms of the free fall aspect. So here we have Duke Kaboom's going to set up on a ramp. So let's draw his little ramp over here. Okay. And it's at the top of the RV. Okay. And that RV is 1.25 meters above the building that he's trying to reach. That's over here. Okay. So we have a distance of 1.25 meters. We are above the other location we're trying to get to. Okay. So his motorcycle can get the speed of 13 meters per second. So we're going to go off this way at 13 meters per second. And the ramp is an angle of 36.5 degrees, okay, to the top of the RV. So the question becomes, if this is 7.55 meters away from one thing to the other, will he make the jump? So we need to know, is he going to go, if he jumps off here like this, or is he going to land short? What's going to happen? What's going to be the end result of this whole thing, right? So think about that. We're trying to find out how far away he's going to land when he does his jump. So if we're looking for how far away we're going to land, of course, then we're always going to be looking at our dx. How far away are we going to land is the distance in the x-axis. And since our horizontal motion is always constant, dx is vx times t air, right? Those are the two components. For horizontal motion, how fast we're moving horizontally times how long we're in the air for. Okay, good. Let's find Vx. We know how to find that. Vx is going to be V times the cosine of theta, right? That's going to tell me how much of that velocity initially is going in the horizontal direction from that 13 meters per second. We'll come back and solve that later. Let's figure out what else we're going to need. So compared to our problems where we kind of went from ground to ground, T air is going to be a little bit different here. We went ground to ground, so kind of draw a separate one here. So if we were going ground to ground, remember, we could just find the time it took to go up and multiply it by 2 because it was the exact same as the time to come back down from that peak, right? However, in this case, that's not true anymore, right? Now we no longer have those two values being equal. One is greater than the other. Okay, the time it takes to go up is going to be less than the time it takes to come back down because of that difference in height. So we need to separate those two and figure out what they are individually. So time in the air is going to be equal to the time it takes to go up plus the time it takes to come back down. Okay. Now, on the way up, we've been doing this. We're using our Vf minus Vi equation over G, just like we did in free fall. Understanding the fact that when we're dealing with the vertical motion, which is the way up, when we care about the vertical motion, we're finding time in the air. That final velocity is going to be 0, okay, because we're talking about the peak up here of the motion. Again, we're talking about the motion from here to here, okay. So at the peak, our vertical velocity is 0. Our initial velocity right here is not Vi, but it's actually, this is really Vy. So our equation for the time to go up is whatever our y velocity is initially divided by the acceleration due to gravity. So that's going to help me find the time it takes to get up to the peak of the motion. Well, to do that, we need to figure out what Vy is, of course. And that's given by our trig functions again, v sine theta, the vertical component of our velocity. So again, reminder, we have our 13 meters per second, and the horizontal component, that's the Vx, that's our v cosine theta, and the vertical component is that Vy, that's the v sine theta from the vectors. So now we have our time it takes to, we can find our time it takes to go up as soon as we find Vy. That's great. How are we going to find our time it takes to come back down? So here's where, recalling again, we're talking about something coming down from that peak, and we're only talking about the vertical part of the motion because time in the air is only dependent on vertical motion. Okay? Horizontal part of the motion doesn't affect it. Okay? We want to know basically the time it takes to fall. Because remember, the time it takes to come down from here is the exact same for every single one of these different pathways, and the time it takes for something to fall is always going to be the square root of 2 dy over g. Okay? Use that equation a bunch. That's going to help me find how long does it take me to come back down to the ground. Okay, great. I can find the time it takes to fall if I know what dy is. That dy, let's get rid of some of these pen marks on here. Let's get rid of this one, get rid of that one, that one. Dy, let's get rid of this one too. Dy is that distance from here to here. It is that height at the peak. That's what we need to know. This is the dy we need. Okay, that's how that's the height we need to figure out how long it's going to take to fall. So, how are we going to get it? Well, there's a couple different ways we could do it. Okay. If we go back to our free fall equations and think about what we know do we know vertically about the motion of this object? Okay, getting up to the peak. Well, we know it's starting at some position off the ground. Remember, we call that our DO, where we're at initially. And if we want to know up here, we know the velocity up here is 0 meters per second. We know the velocity down here is some initial velocity, right? And if we know final and initial velocity, we found our equation earlier where the distance is vf squared minus vi squared over 2g. That's what was going to help me figure out how far I went. And again, to compensate for the fact that we're off the ground, we're going to have to add a DO into that. Okay. However, we go back and look at our equation and our values and what VF and VI and DO really are. Well, VF is 0, so it's going to go away. VI again is VY, just like it was for the other one, because remember, we only care about that vertical part of the motion. We're talking about height. Horizontal part's not going to affect it. We only care about that vertical component, that VY. We're going to divide that by 2g, and then we're going to add in that initial height that we started at. Okay, so we've taken that equation we used in free fall and we transformed it into our component with our component velocities to find whatever that peak height is going to be. So that dy, that peak height, is going to be vy squared over 2g plus the initial height of the object. So now we have the components we need to solve what we're looking for, because we know to get distance in the x-axis how far it's going to go. That's going to be this equation right here. There's one. That's our end goal. dx equals vx times dr. How far do we actually go? Well, vx we can get by v cosine theta. Time in the air is going to require two parts. It's going to require time up. It's going to require time down. We found t down is going to be, after we focus on just the y-axis, we found t up is going to be vy divided by g. Okay, we replaced all of that, and we got vy divided by g. Well, we can get vy by doing our component vector, find v sine theta, okay, find out what vy is, find out that vertical component of the velocity. And then we can find the then we need to find the time down, and that time down is going to be based off the square root of 2 dy over g. Okay. And then we need to figure out, okay, that's great. I need dy though. Well, dy is going to be based off how fast we're moving initially vertically and the initial height we start from. And from here, we just go back and plug all our numbers in and get our solutions. So we would have vy squared. Vy, well, we need vy. So vy is v sine theta. So let's go here first. So this is 13 sine 36.5 degrees. And if we plug that into our calculator, we find out that the vertical component of the velocity is 7.74 meters per second. Okay, so we take that over here, 7.74 meters per second, and we're going to square that, divided by 2 times 10 meters per second squared, plus that initial height we start at, which is the 1.25 meters, tells me that we are going to reach a maximum height of 4.25 meters above, not above the ground, but above the carnival stand, right? That's how high we're going to go. So the next question becomes, okay, well, if that's the case, how long is it going to take me to come back down? And when we go here, square root of 2 times 4.25 meters, all divided by 10 meters per second squared. Okay, and if we do that, we find out that it's going to take 0.92 seconds, 921 seconds, for the person to land back down on the ground. So now we found the peak height, we found the time it takes to come back down, we found the initial y velocity. Well, now we can find the time it takes to go up, and that's going to be 7.74 meters per second divided by the 10 meters per second squared, and that's 0.774 seconds. Okay, so it's going to take 0.774 seconds to get to the top, 0.921 seconds to get back down. So the total time in the air is going to be 1.70 seconds. Okay, so now we know how long Duke Kaboom is going to be in the air for. Great. That's half of our equation up there, right? Our end goal. But we still need Vx. So we go back, let's go back to our trig functions. We know our V is 13. We know we're at the cosine of 36.5 degrees. And if we work that out, 13 times 36.5 cosine equals 10.5. And that number makes sense because it's more than Vy. It should be more than Vy since the angle is less than 45 degrees. And then we go here and we plug in 10.5 meters per second. And that's going to be times the 1.70 seconds. And we do 10.5 times 1.70. We find out that easily clears by traveling a total distance of 17.9 meters. Okay. So there's a lot of steps, a lot of components to it, but all it is breaking it down into the things that we understand already, right? The end goal is the same as it's been with every other projectile problem. Knowing dx based on vx in T air just becomes finding those individual components based on things we've talked about in free fall and everything else as we've gone along the way. So hopefully this makes sense, and hopefully you can use this for helping you work through the practical exam.